All right, starting out, and let me get my DQO thing open. Oh, what am I thinking? I need the white paper. All right, everybody should really take out their white paper, as we're gonna, the slides here don't encapsulate all of the details that are going on. Now, we looked at the DQO process yesterday, and we looked at the 7 stages. Within each stage or step, there are actually usually multiple functions that have to take place. And we're going to start here on page 53. Okay. And the scenario is that there's a company that is doing a composting, and basically they're trying to follow the 40 CFR Part 503 Subpart D requirements for controlling pathogens and vector attraction, and to achieve Class A status, which is basically unrestricted. Is that a fair statement?
Unrestricted use of biosolids.
Okay, good. So they need to achieve and maintain uninterrupted temperatures above 55 degrees Celsius, or about 130 Fahrenheit for 3 consecutive days. And that, as they say, will knock out all the pathogens. And so we start with step number 1, state the problem. There are really several stages here. There's a problem description, there's establishing the planning team, and there's defining the conceptual model. Okay, we've actually discussed all those, but now we're going to try and do this in a semi-real context. The problem description is basically that they need to develop a cost-effective system to monitor the composting piles so that they can meet the requirements. Okay, that's fairly straightforward. We reiterate in there some of the aspects that there's standards, there's time and temperature constraints, and the scope of the DQO process will be to develop the procedures that verify temperature data meet the regulatory requirements. Okay, and the reason we want to do this with temperature data is that the alternative is sampling. Okay, that's going to be a lot more expensive than just taking temperature measurements. So that's our problem description. We have to meet the requirements. It's all about temperature and time, because otherwise then we go to the more expensive method of laboratory analysis, or we just punt and say, sorry, it's waste. We'll pay for it to go to the landfill. Okay, so there's sort of 3 options. Make it good, or make it maybe good and sample and try and prove it that way, or just send it off as hazardous waste. Now, we have a planning team to organize. We proposed a 5-member planning team, and those members include the plant manager, the plant engineer, a QA/QC specialist, who's actually a contract person. It wouldn't have to be, but we just did that kind of for variety. A biologist who's also on contract and has lots of laboratory experience. And you always need to define the prime decision maker. Somebody's always going to be in charge. And that could be the plant manager, as it is in this case. It could be whoever you want. Now, the plant manager may or may not have access to the checkbook, but he has access to the person with the checkbook. So somewhere along the line, you got to have connections to the money, because there's got, what do they say in the right stuff? No bucks, no Buck Rogers. You know, no bucks, you don't get your DQOs. All right, now I'm going to have you correct me if I'm wrong. What is your analysis of this planning team? Okay.
Well, I think it's pretty good, and I think it's going to be site specific. I mean, I think a small town is going to have a different planning team than a larger city, but one of the things is you want diversity from the engineer to the operator, I would think, when you're putting together a sampling
Very good. Now, I'm going to make a couple of comments too. One thing, there is no statistician in this particular thing. Now, you don't have to have one. The EPA usually recommends it, but you don't have to have one. So I'm going to point out some of the flaws, because as I said, I wrote these stream of consciousness. This one I intended to put in, but we might want to consider that for the final version. The other thing I'll mention, Trust was talking about city people and so on. This is a private group, okay? And it may be a different organization and structure for if a city is doing the DQOs versus a private company doing the DQOs, okay? So, you know, just little nuances here that are going to come up in real life situations. Now, I can't do every situation, but I just wanted to point out that what she called our attention to a city doing this versus what I've written, a private company, is going to be slightly different. Yes?
What's the split house?
And just point of order, on page 11 of the white paper is an example cross-section of a static aerated pile. You can see basically, as Tressa said, it's got a little blanket, so to speak, over the top, which kind of keeps things, hopefully keeps the heat in. You don't turn it as you do. We saw the Scarab at Pueblo Chemical Depot. That mixes it up. Okay, that's the difference. This one sits and cooks. The other one, you keep turning and mixing. We can see that, you know, inside it's all cooking, but we do know, for instance, that on the edges, especially at the bottom, things can be cooler. So we want to be measuring there. That's going to be part of our DQO process. We're assuming the central core is going to be the hottest. Okay, but as we mentioned, if there's not the right conditions, there could be issues there. So my scenario, and we can critique that, puts most of the samples in cooler areas, top and bottom, sides, and so on. But we check the middle at about one half the rate or 1/3 the rate, and just to be extra sure. I'm not a composter. That may be overkill, but that's the way it is. We can discuss that. But that is a conceptual model. It's actually fairly simple. Okay, usually it's a lot simpler than most environmental models where you have groundwater flow and all that kind of stuff. But that doesn't make it all that much easier, because there's still stuff going on that we need to measure. Okay, so are we good with conceptual model? Good. Okay, well, let's keep moving here. Step number 2 is to identify the goals. Under here we have 3 items: the principal study question, the alternative actions or outcomes, and then a decision statement. So this principal study question is, does any portion of the pile fall below minimum temperature during the 3-day exposure period? It's fairly straightforward. That's really our key, because that's what drives compliance. And this is, I guess that's really all we need to say about the goal, unless...
Yeah, if it doesn't meet it, you either have to start all over or abandon the pile.
Right. Okay, so that's straightforward. Alternative outcomes is that it could dip below 55 degrees, and then you have to reset the clock, which is probably not what you want to hear. Along with that, an outcome, I guess, in this section was what we're calling a T55 chart, and we're assuming that you're going to take more than one temperature reading in the pile, and so lots of locations. And if they're every hour or whatever time increment you happen to select, we would ask you to report the lowest value and chart that, so that you can see when it crosses, the lowest value crosses 55 degrees, and then the lowest value. Otherwise, you'll have, if you're taking 100 samples or 100 measurements or even 10, you don't want 10 measurements every hour, just one. So we plot the lowest, and then you can do that time series graph, even in Excel, over time, and show that it maintained a plus 55 temperature for the 3-day period. And that'll serve as a record and documentation, which documentation is such an important part of the DQO process as well, and it'll be important for regulatory approval, I assume.
Well, yeah, and in fact, that's how you prove that you're following 503 for pathogen reduction, and this, I think that's where we want to be with this case study.
Okay. Based on that, our last issue is to make a decision statement. And basically, it's if no temperatures occur below 55 degrees during the composting period, then it's okay. Then it meets the Class A requirements. So that's a fairly straightforward decision statement.
Can I just briefly
Okay, step 3, information inputs. This is fairly simple. We only need temperature data. Now, how much, we're not quite sure. How often, we're not quite sure. But we need temperature data. The good news about temperature data is it's not like laboratory analysis. Okay, we don't have to design the sample. We don't have to worry about the equipment and all that. Temperature is pretty controlled. We understand that very well.
And Jeff, aren't there like, I mean, can't you just do continuous monitoring if you want to?
That's the way I had it set it up. Because I do continuous monitoring, I don't know if they actually do that in this industry. Certainly, I'm sure it could be done, whether that's economic or practical, I don't know. Personally, I thought it'd be easier to set up a grid and let it monitor continuously than send someone out once an hour, take a whole bunch of readings. But I don't know. That's very good. Okay. Number 2, under information inputs. What are the basis of the information determination? Basically, we're just following the rules in 40 CFR Part 503, if I'm not correct. So fairly straightforward there. Sampling and analysis methods. Temperature data will be obtained using temperature gauges in the pile. Whether they stay there or are put in periodically, that's subject of debate. It says here, I was recommending continuous monitoring, which in theory, you can collect data every second if you want. I think that's probably a little excessive, but if you want proof, you could do that. And computers really don't care too much about data. They collect lots of it these days. So, let's see, where are we going here? 55. Okay. Defining the boundaries. Well, the target population is the whole pile. I think in a windrow you might be able to divide it up a little bit, but I think with an aerated static pile, it's got to be the whole pile, all or nothing. Okay, and the sampling unit and the decision unit are the same thing. It's the whole pile. Temporal boundaries are very specific. As per 40 CFR 503, it'll be 3 days above that temperature. Okay, and I don't have any idea that, you know, since they get a little longer to do the VAR. Right, and we did limit this case study to the pathogen kill, not the vector attraction, because that's the whole section, and then unfortunately that would probably need its own DQOs. So it seems to me there should be some discussion also of the largest particle size of the amendments. Because that, if they're too large, correct me if I'm wrong, they could be a source of cooling. Say a big wood chip, okay? Well, that's partly why we're here. Because I've come up with a conceptual model of what I think might work, and we'll take a look and tear it up and try and improve it. So let's move on to step 5, develop the analytical approach. The parameter for decision making is essentially going to be your percentile. We need 100% above 55 degrees for 3 days. Of however many probe measurements we take, all of them have to be above. So the percentage is non-negotiable, it's 100%. That sort of keeps it simple. And that follows, the decision statement follows. If all the temperature readings are above the critical temperature, then we can declare that to be Class A material. So in a sense, that's a fairly straightforward program.
Perhaps a different,
This is sort of one of my questions too. As Tressa said, and it was a little surprising to me, the guidance really doesn't say a lot more than representative sampling is necessary. And that's pretty broad. I didn't see a case study saying, here's an example of how XYZ facility did representative sampling. So, what we have in here is just, I'm swagging it. And so let's take a look at that. We'll take a look at the pictures. That'll help. But step 6, the decision rule is if 100% of the temperature readings met or exceeded the critical temperature, then we're good to go. Otherwise, we have to reset the clock or send it off to the landfill. Okay? And it's probably one of the more straightforward decision, given the fact that temperature readings, it's not like a lab analysis. There's no quibbling with the temperature reading. And if they don't all, it's a very simple, straightforward result. Okay, so, all right, data collection plan. Here's the final product. Okay, basically, I was envisioning a three-dimensional sensor array, and claiming that that was going to be sufficient to characterize the temperature distribution within the pile, understanding the conceptual model that the edges, bottom, top, and so on are going to have the lowest temperatures and expecting the highest temperatures in the middle. We're going to monitor both the high and low temperature zones, and we're going to put sensors at the base of the pile about 12.5 feet apart along the axis. We're going to put sensors along the base and the top. We have base array, center array, and cap array. You can see that in figure 54. I'm on page 56, by the way. I should mention that. And so you can see that we're getting the ends, the top, middle, and bottom of the exterior on both ends, and then we're getting kind of top, middle, and bottom of 3 interior locations. And in theory, the interior locations should be okay because they're not the very coolest, but as a doubting Thomas, I confess, I think it's appropriate that we at least take some number of samples, whether they should be every 10 feet, every 12.5 feet. I said not more than 15 feet apart. I picked that out of the air, okay? But it just sort of happened to fit my design with a 50-foot pile. Someone could say, Jeff, you don't know what you're doing, and they're right. But but that's what I picked. And that's sometimes what DQOs are, is like, all right, here it is. Tell me how I need to fix it. Okay, so that's why we're here today, and hopefully Tressa or somebody can help us. Again, we've got the cross-sectional view as well. You can see that basically you've got 6 samples on the edges and then 1 in the center, base, center, and cap array, plus a central core array, which is a lot smaller. And we find out that, basically you're taking, how many samples at a time? 35 sensors, I'm saying that you should put in there and monitor continuously, okay, every hour. So every hour you get 35 readings. You're going to do this for 72 hours. You get, well, if you take temperatures for 1 week, assuming it takes a couple of days to come up to temperature, 7 days, you're going to get almost 6,000 temperature readings. That's a lot. I don't even know if it's enough. You could argue, what happened? Maybe what if it dips down, toward 56, and it stays at 56? Did it go and come back up over the hour? I don't know. There could be questions. Because it's a 100% rule. It's very unforgiving. What do you say?
Yeah, but the pile is represented.
And you brought up a good point. What is the level of interest and concern from the regulator? You know, there are regulations and then there's enforcement of regulations. Sometimes those don't quite jive with what you think you might expect. Some regulators are a little more lax. I mean, I know at the Savannah River site, you know, sometimes they're so confident in what the operator is doing that the regulators don't pay that much attention for a while, okay? And everything goes fine, okay? And that's a nuclear site, so that, you know, things can go wrong, and when things go wrong there, it's a bad day, okay? But it's a bad day here if the temperature falls too. So those are some of the, again, human factors that fall into that, and that's kind of beyond the scope of DQOs.